Pleasure to be invited yet again for such a good conference. Unfortunately, I can't be there in presence, but I will extend my kindest gratefulness to Dr. Ballerau and Michelle Pagad, who organized this kind of video conference so I could participate in the conference. Anyhow, coming to talk now. I'm going to talk about the Plasmon Enhancement on Semiconductors for solar energy technology. And this combined work between Imperial College London and London South Bank University, which is two universities been in a very, very close relation for 7-8 years. So I also have some of the main contributors for this big collaborated work. So the outline, I'm going to talk about surface plasmon resonance and how the relation to solar light and how we can increase technology. So the whole aim of the research is looking at the, for example, we have two routes to go down, like thinning photovoltaics and also using solar-driven photocatalysis. We're going to have these two aims to improve them, and we then start by looking into manufacturing different arrays of gold and silver, nanoparticles on semiconductor surfaces, and then the evaluations for such detector. We're going to then verify with theoretical models to describe what the mechanisms are and how we can improve that. To start the whole process, we need to understand what surface plasmons is. And really, to make it very short now, I'm going to explain that this really is like the free electron plasma around metal nanoparticles, how they're oscillating. So the surface plasma oscillates them with the electromagnetic field, i.e. the light that we're interested in. And we can relate it to a dipole resonance. And with that plasmon, it's actually the quantum of this plasma oscillation. And how the free electrons, how they're oscillating together, when they couple with the incoming electromagnetic field, we're using that to describe what will happen when it goes into resonance. And the most of the focus will be in the resonance of this plasma oscillation. We call it plasmon. And now we're going to put them on a semiconductor surface. So we work with silver and gold nanostructure, and we're looking how they be affected on different semiconductor surfaces. And what we're going to do, we're going to talk about localized surface plasmon resonance, the whole field distribution, what we see here like in the spherical metal nanoparticle, how we get very confined distribution surfaces. It's very localized. And this localized field is coming from these oscillations. It's very defined around the approximately of the metal particles. But we're going to now use that and looking how this localized surface plasmon resonance works on silicon and TO2 semiconductor surfaces. And what we're going to do then, we're taking the knowledge how this nanoparticle exhibit a very strong wavelength specific extinction of the incident light, also an enhanced electromagnetic near field, so the field that I just talked about. We're going to looking at this extinction of the electric field and the near field being formed around this local surface plasmon resonance. And we're going to when this is actually occurring and what mechanism we can kind of subtract from such mechanism. We need to know the exact position for this extinction peak and know how this is varied between the gold and silver, and in particular when they are in nano arrays. So the whole study will combine theoretical description of such mechanism, and we're going to analyze both the near fields and the extinction of light, i.e. the absorption scattering effect very much. And then, as I said, we're going to be the two different metals and two different semiconductors. And long we're going to show the conclusion of how we can improve photo efficiency in two different technologies. The whole concept is like looking into incoming light into a nanoparticle particle structure. We're going to evaluate the kind of amount of backscattering and reflection. We're going to also looking at the oscillation damping, which we call like the loss, which is the absorption of energy, how that can be used, for example, of energy transfer. We're going to look into the transmittance of such structure and also the forward scattering, in particular the relation between backscattering and forward scattering. Then we use these different particles in different dielectric mediums, so we put them down in different dielectric mediums and then see how this whole scenario is changing. We're going to use different architecture like spherical nanoparticles and spherical particles. We're going to put them in very organized array. We're looking at the distance and versus the radius of the shells, and then we're going to put them in different dielectric interfaces, and it's going to maybe air, semiconductor, or maybe having buffer layers in between. We're going to still look at the all contact, the ratio between backscattering and forward scattering, and looking a lot into like how the near field, like I said, which may produce them from the absorption of light. So first, to start this whole big project, we produce different arrays of gold and silver. Just very quickly, I'm going to show some examples what we are doing. In the most common method is using just annealing gold film or silver films, so the same, and to have like a nice distribution of particles on the surface. We've been working in the micellar nanolithography, which is like more or less like using a metal source in a solution and kind of cover them into metals, and then with we can form very, very defined structures on the surface. And with oxygen by etching, we can then take the polymer, and we are left with very, very defined structure of gold spherical particles on the surface. And another one is using nanospherical lithography, where we can kind of, same as using polymer self-assembly, spherical polymer balls, and we're using them as a shadow mask for evaporation. We can have a very nice triangle structure, once again, very good for specific shapes and distance, which is very good if you want to evaluate the near field in between the particles. And this type of self-assembly can be used for a little bit more advanced structures. We can actually them this forming like gold islands. So this is kind of more circular disc on the semiconductor. The good thing here with this type of method is that it's also possible to introduce a buffer layer, such as maybe an ohmic contact, etc. Scanning electron microscopes here are showing just some of the results of the different methods. The film annealing, as you can see, is to find like a nice distribution of approximately 120 nanometer gold hemisphere on the surface. So it's a large structure. This is good if you want to kind of mimic silicon wafer or like solar cell structures. And the nanolithography, as I said, this is very good if you want to evaluate very specific space in between them. You can't do that in large areas. And here's an example of the gold disc, which is the circular disc on the surface. Examples of the triangular shapes from the nanocoidal lithography. And here in the corner you can see some example of the work we're taking currently at Imperial College London, where we're looking at different structures of the triangle structures. We're using a lot for the near field and the fluorescent response biosensors, for example. So now back to the whole technologies we're looking into. For 10 years ago, there was an absolute article by Atwater and Pohlman, which is called Plasmonics for Improved Photovoltaic Devices, and he describes in details how surface plasmons can be introduced into when you're thinning, and how you can then, by utilizing the surface plasmon scattering effect, you can then improve the light utility in a thin silicon structure by the scattering. And it was also describing how embedded, you can also utilize the near field formation around the particles. Since then, really the last 4 years, many research groups have looked into spinning of the solar cells, in particular silicon, because the crystal silicon is the high efficient, relatively cheap, but if the high efficiency found in crystalline silicon, very attracted to thin down the silicon, thinning it down, and using smart architecture, for example, that when you thin down, the incoming light will be transmitted straight through, using also the absorption in this case is quite poor, and you're losing a lot of the infrared light, so the photon efficiency is heavily reduced. But by using smart architecture, by utilizing Plasmon input on the backside of substructure, you can then kind of promote what they call forward scattering, i.e. like the scattering kind of encapsulated light that should otherwise have been lost in the transmittance. Now into the other technology we're looking into, which is visible-driven photocatalysis. In particular, we use the water splitting as the aim of the whole research, but really it's a solar-driven photocatalysis. And normally, in photocatalysis, the most standard semiconductor to use is titanium dioxide. We have a band gap of approximately 3.2, unlike silicon, for example, it's got 1.1. What that does, mostly the light will only be absorbed in the ultraviolet section of the solar light. Utilizing the local surface plasmon, i.e. placing like a surface plasmon on the surface, we can then utilize absorption into the visible light, and them together we are spreading reactions of a greater rate of the spectrum. So that was the aim of this route of the technology. And for solar cells, we were looking into the scattering mechanism. Here we're looking in the photocatalysis, we're using much more the knowledge of the near field formation, close in the localized surface plasmon in the near field, in a very close proximity of the nanoparticles on the semiconductor, which in this case will be a titanium dioxide. We studied different mechanisms for such for enhancement in the photocurrent in a photocatalytic system. And the different mechanisms we studied were typical hot electron injections or direct electron transfer, which is electron transfer from the gold particle into titanium, or maybe looking into plasmonic resonant energy transfer, which is the energy transfer between the gold and the titanium, or like spot heat effect, which is like kind of the temperature difference caused by the near field. We used the different models to describe what we saw experimentally. So that's now to some of the early studies we did on the solar cells, where we used the theoretical models for describing the scattering. This is now being tied together over the years. So for you to understand how the process of working with the theoretical models, for example, we used like the Druid to looking at the dielectric function of, say, a surface plasmon resonance, like a gold spherical particle, or and we're seeing that, so we can get an understanding how the dielectric function is varying over different shapes and spaces and methods, and we can get then expressions of the absorption and scattering cross-section, i.e. the radius this mechanism is happening, which is much larger than the actual particle size. I think this is the fundamental understanding of the localized surface localized plasmon resonance to evaluate the dielectric function of different wavelengths and over this shapes and space. Then what we're putting in now a particle of interest, putting them into like a lower boundary condition, and use finite difference time domain method. All of a sudden now we can looking at the power distribution of backward and forward scattering, and it would define boundaries. And do that, we can then describe. So we're looking here at extinction spectra over wavelength. If when we evaluate the extinction of the incoming light, we don't know which ratio it is of scattering and absorption, but thanks to this model we are able to do that. And we can see that it's varying over the wavelength, and it's varying particle size and material and shape. And to do that is like you can then use your predicting DT models and verify the experimentals. Quite standard optical measurements, such as we're using monochromatic measurements between 400 and 120 nanometer, which means covering the whole solar light, and in connection with IV measurements with and without incoming light, and also normal spectroscopy with reflectors. Here, just example that the transmission wavelength for different particles and reflectance wavelength, they do look different. They are different because we can then extract different information. For example, from the transmissions, since we get the information on how much is forward scattered and how much is absorbed, and also the reflectance, we can then say, sorry, this should be the other round, this should be what is the back scattering but not forward scattering. So it's confirming our model. We work very close to experimental results and with the theoretical models. And further, we also we continue our models of like looking into, for example, using different buffer layers. Here you can see just like some hemispheres on a silicon surface, and we have evaluated then that just replacing your particles on the surface, the more dominant scattering effect is going backwards, so called backward scattering. But by introducing different thickness of a buffer layer of an oxide, we can then increase the ratio of the forward scattering, and this is exactly what we want with the thinning of the solar cells. So coming back now to for the photocatalysis, and so we have understood now very much how to direct the forward scattering to thin solar cells, and in particular working with silver on silicon cells, and we understand the mechanism how to obtain highest efficiency by using some of our knowledge of extension of the incoming light into photocatalysis. So the point is, like, our knowledge is that if here's gold particles on a titanium photocatalytic surface in a nice array, our knowledge was that the extinction of the incoming light has got a peak around 800 nanometers. This is by the titanium. This must have been done from the surface plasmon. But the increased in photon to current efficiency percentage, we all have a peak exactly at the same peak position as the surface plasmon. We learned that it's probably due to the plasmon combined with the TR2 that increased a photocurrent, and this will be then attracted in solar light-driven photocatalysis. So we use this knowledge, and we now using our understanding of how adapt different models the dielectric function and evaluating cause mechanism of the increased photocurrent. We were not really sure exactly what it was. So we're starting into what the different mechanism could be. For example, if there should be a direct electron transfer between the gold and the TR2 surface, we started with the possibility of such mechanisms. We see just like the different potentials we need for driving it in the gold particles, and here's the conduction band and valence band of the titanium. And we saw then that it is driven most stably by a Schottky barrier, but we see any effect. There could be it should be electron transfer. If that was a mechanism of it, there should be an electron transfer as such, we should see a depletion in our gold particles, which we didn't see, which you can use the me theory, for example, to see the change of the peak. But we didn't see that everything was pointing against it. And we looked into maybe it's an energy transfer, maybe something of the near field being formed in close proximity to the interface. So we started looking into different, for example, like FRET, which is first is resonant energy transfer. This is a mechanism very commonly found in organic solar cells, for example. But for inorganics, such as TR2, we realize the absorption of TR2 and the absorption of the gold particle have a little overlap. So the ground for like have a feasible energy transfer was very, very small. We continue still working with the different models of describing if this what we see then is foreign to be maybe caused by other kind of near field. By we to models of explaining if they feel causing like a charge separation, i.e. forming electron holes in the TR2, which of by the near field. And that could have been something to do with the increased photocurrent. But really, we couldn't still find any. There might be that this whole mechanism of increased photocurrent and gold on TR2 for the photocatalytic purpose. A combination of different mechanisms, but we have not yet found a mechanism that fits the bill. Electron transfer to there was lots of things talking about against it, and this was like I said, the whole idea is like it's a shotgun very driving it. We were all looking into maybe electron tunneling between the space charged region and the TR2 and the metal, and also because less proofs of this actual electron. We also will start working with maybe there's something of the interfacial problem between an oxide and a gold. So we're looking at the different ohmic contacts. That's why we manufacture the circular gold discs on the TR2. We're going to increase an ohmic contact and see if we can improve some mechanism or we can identify it. But so far we could not see evidence of an electron transfer. Some results undertaken in Imperial College is now summing up the conclusion from the two lines of using like the future of solar cells and the future of visible light-driven TR-based photocatalysis. It sums up together of some of the latest work which is undertaken between the two universities, and that is like looking into more like the hot electron transfer. Some of those we can see here. This is the absorption of a wavelength on different gold particles on gold. Really just put it into attention of that. Once again, what we get the extinction peak and the absorption peak around 100, and when we evaluate it now, not like before, evaluated by photoelectric chemical cells, we evaluated by FDT calculation. We were able to identify the same photo current increase, and our plausible mechanism for the increase is now a big portion of so-called hot electron transfer. So this hot electron transfer, hot electron transfer can be seen as an analog as a thermodynamic heat engine. It's kind of driven, so we kind of creating electrostatic energy, a little bit like a heat engine, but instead of producing mechanical work from an entropy change and a temperature change, we then, instead of doing mechanical work, we are producing electrostatic energy. Flavor we are working for the moment, and all basic conclusion is like the plasmon decay, like the damping of the oscillation, generate a hot electron in the metal. With the sufficient momentum, an electron can transfer into the conduction band. But we don't really still not show exactly how this electron transfer occur, but most definitely the whole electrostatic force transfer may be driven by the hot electron mechanism. So the whole conclusion, now we're summing up from coming from thinning of the solar cells and using visible light photocatalysis, is we're looking in different metals. We have got a very clear understanding of models and theoretical to describe plausible mechanisms for any an electron transfer, or like forward and backward scattering, which is very much in the solar cells. We can see them, for example, localized plasma reference. In that case, such scenario, absorption is less for silver particle. You know, the scattering effect will be higher, and this is exactly what we need then for thinning of solar. If we want to work with encapsulating more scattered light in a thin structure. But gold and silicon, that gold and silicon combination is like all forming a very deep level within the silicon band, so it acts like a recombination center, so the total current yield will be hence much smaller. Look, gold localized plasma surface reference that we saw here now what we are studying now in 2014, then it most definitely is producing hot electrons. Gold is very suitable for this case because it's got high absorption efficiencies. When we're using that for the theoretical models, so for example, the Drude models for explaining the dielectric function in this, so we're using the Lorentz model expressing it, and we can see how this like the incoming wavelength and how which region it can work. And solution is that scattering mechanism with that silicon on silicon to be architected to increase the forward scattering and increase the scattering cross-section, and can improve the best eye performance in thin photocells. And then you on the wide bandgap semiconductors such as Ti2. This could be if we want to utilize hot electron transfer. So it's the whole idea of this research is to understand mechanisms across an interface, mechanisms of energy and electron transfer, and we can improve different plasma technologies such as solar photocatalysis or photovoltaics. So for your attention.
Anna.
Yes.
It's excellent work that you're doing. Very can. A question is that has technology been commercialized, or is it just at the experimental stage?
First of all, now, because two technologies I'm talking about here, I would say that more mature technology is, of course, the scattering effect in solar cells, which is, I would say, commercialized may not. Yes and no, it's much more mature and it's well understood. The relationship of the thinning of solar cells utilizing the surface plasmon as to how we can link that with visible photocatalytic active technology, which is not commercialized and is still in its very, very early days, and it's because no one really understood the mechanism for the increased. There may be an increased photo efficiency, but no one really understands yet how. So, yeah, for the solar cells, yes. For visible light driven photocatalysis, no.